Welcome. This is your boring lesson for rest and sleep. I'm Man. If your day has been long, busy, or heavy, you're exactly where you need to be. Today, I'm going to take you back to the most boring periodic table lesson from high school through a simple relaxation exercise. I'll guide you into the same monitorial lecture your mind already remembers. Your body and thoughts will drift into that familiar sleepy, relaxed state without you having to try. This isn't a story you need to follow closely. You don't need to stay awake. Just let the sound of my voice be here with you. Before we begin, let's make this space quiet and uninterrupted. If you can, turn on Do Not Disturb now. And since you are watching on YouTube, it helps to turn off autoplay so nothing pulls you back out of sleep later. If these nighttime stories help you rest, you're welcome to like the video or subscribe. No pressure at all. Now, let's get comfortable. Lie down or sit back. Feel the surface beneath you. The bed, the couch, supporting your weight. Notice the temperature around you and make any small adjustment you need. When you are ready, gently close your eyes. We'll start by relaxing the body, one piece at a time. First, gently tighten your face. Scrunch your eyes, your cheeks, your jaw. Hold. 3, 2, 1, and relax. Let your face soften completely. Now, lift your shoulders up toward your ears. Hold. 3, 2, 1, and let them drop. Feel the release through your neck and across your upper back. Now, point your toes toward you, tightening your feet and lower legs. Hold. 3, 2, 1, and release. Let your legs grow heavy, still at ease. Take a moment to notice how your body feels now. Heavier, quiet, more settled. Now we'll slow the breath. I'll count for you. There's nothing you need to remember. Breathe in through your nose for 4. 1, 2, 3, 4. Hold gently for 7. 1, 2, 3, 4, 5, 6, 7. Breathe out slowly through your mouth for 7. 1, 2, 3, 4, 5, 6, 7. Again, in 2, 3, 4. Hold 2, 3, 4, 5, 6, 7. Out 2, 3, 4, 5, 6, 7. One last time, in slow and easy. Hold. And out. Let your shoulders soften. Your jaw loosen. Your body sink. Now, let your breathing return to its natural rhythm. You are support. You are safe. You don't need to stay awake for this. Just rest and let the lesson begin. Close your eyes. Now, let's walk together into a familiar classroom. Find your usual seat, the one your body remembers without thinking, and let yourself sink into it. Around you, there's the low, distant murmur of students talking, voices blending together until they fade into the background. The air feels familiar. The room feels safe, predictable, almost dull in the most comforting way. The lesson begins.
We will begin, as most chemistry lessons do, with the definition of an element. An element is a substance that cannot be broken down into simpler substances by chemical means. Each element consists of atoms that all have the same number of protons in their nuclei. This number of protons is called the atomic number. The periodic table is arranged in order of increasing atomic number, which means from the lightest element, hydrogen, which has 1 proton, to the heaviest elements, some of which have over 100 protons. The atomic number determines what element we are dealing with. It is the identity of the element. Each box in the periodic table contains specific information about one element. This usually includes the element's symbol, atomic number, atomic mass, and sometimes additional data such as electron configuration or oxidation states. The symbol is usually 1 or 2 letters derived from the element's English or Latin name. For example, hydrogen is represented by the letter H. Helium is represented by He. Sodium, which comes from the Latin word natrium, is represented by Na. These symbols are standardized by the International Union of Pure and Applied Chemistry, which is often abbreviated as UPAC. The layout of the periodic table is designed to show patterns in element properties. The horizontal rows are called periods. There are 7 periods in the modern periodic table. As you move from left to right across a period, the atomic number increases by 1 with each element. This means each element has 1 more proton and usually 1 more electron than the one before it. The vertical columns are called groups or families. There are 18 numbered groups in the standard periodic table. Elements in the same group tend to have similar chemical and physical properties. This is because they have the same number of electrons in their outermost energy level, also known as the valence shell. The number of valence electrons is crucial in determining how an element reacts with others. For example, all elements in group 1, known as the alkali metals, have 1 valence electron. This makes them very reactive, especially with water. Lithium, sodium, and potassium are common examples. Group 2 elements, known as the alkaline earth metals, have 2 valence electrons and are also reactive, though less so than the alkali metals. Group 17 elements are called halogens. They have 7 valence electrons and are very reactive nonmetals. Group 18 elements are the noble gases. They have full valence shells and are generally unreactive. This group includes helium, neon, and argon. The periodic table is divided into blocks based on the electron configurations of the elements. The S block includes groups 1 and 2 and helium. The P block includes groups 13 to 18. The D block contains the transition metals, which are found in the center of the table from groups 3 to 12. Finally, the F block, which is usually shown below the main body of the table, contains the Lanthanides and Actinides. These blocks reflect the orbitals that are being filled with electrons as the atomic number increases. The transition metals in the D block are known for having multiple oxidation states and for forming colored compounds. Examples include iron, copper, and nickel. These elements are often used in construction, electrical wiring, and catalytic processes. The Lanthanides are sometimes called the rare earth elements. They include elements with atomic numbers from 57 to 71. The Actinides include elements from atomic number 89 to 103. Many of the actinides are radioactive, such as uranium and plutonium. In the early 1800s, scientists began to notice patterns among the elements that were known at the time. Dmitry Mendeleev, a Russian chemist, is often credited with creating the first widely recognized periodic table in 1869. He arranged the known elements by increasing atomic mass and noticed that elements with similar properties appeared at regular intervals. He even left gaps in his table for elements that had not yet been discovered, and he accurately predicted their properties. Later, it was discovered that arranging the elements by atomic number rather than atomic mass produced a more accurate organization. This led to the modern periodic law, which states that the properties of elements are a periodic function of their atomic numbers. Atomic mass, or atomic weight, is also listed in each element's box. This value represents the weighted average of all the naturally occurring isotopes of that element. Isotopes are atoms of the same element that have the same number of protons, but a different number of neutrons. For example, carbon has several isotopes, including carbon-12, carbon-13, and carbon-14. The atomic mass takes into account both the masses of the isotopes and their relative abundances. Each element also has a specific electron configuration, which describes how its electrons are arranged in shells and subshells around the nucleus. The electron configuration influences the element's reactivity and its place in the periodic table. For instance, the noble gases have full outer electron shells, which makes them stable and unlikely to form compounds. On the other hand, the alkali metals have one electron in their outermost shell, which they readily lose to achieve a stable configuration. The periodic table also provides information about trends in element properties. These trends include atomic radius, ionization energy, electron affinity, and electronegativity. Atomic radius generally decreases from left to right across a period and increases from top to bottom within a group. Ionization energy, which is the energy required to remove an electron from an atom, increases across a period and decreases down a group. Electron affinity, the energy change that occurs when an atom gains an electron, tends to become more negative across a period. Electronegativity, which measures an atom's ability to attract electrons in a chemical bond, also increases across a period and decreases down a group. These periodic trends can be explained by considering the nuclear charge and the shielding effect as you move across a period. the number of protons in the nucleus increases, resulting in a stronger attraction between the nucleus and the electrons. This pulls the electron cloud closer to the nucleus, reducing the atomic radius and increasing ionization energy and electronegativity. As you move down a group, the number of electron shells increases, which means the outer electrons are farther from the nucleus and more shielded by inner electrons. This reduces the effective nuclear charge felt by the outer electrons, leading to a larger atomic radius and lower ionization energy and electronegativity. The periodic table continues to evolve. New elements have been discovered and synthesized in laboratories, especially in the higher atomic number range. Elements with atomic numbers 113 through 118 were named relatively recently. These super-heavy elements are unstable and exist only for short periods of time before decaying. Nevertheless, they help complete the table and expand our understanding of atomic structure. The periodic table is not just a reference chart. It is a reflection of the underlying principles of chemistry and physics. It tells us not only what elements exist, but also how they behave, how they interact, and how they form the substances that make up our world. In the next part of this slow and deliberate lesson, we will begin exploring individual groups and families of elements in more detail, starting with hydrogen and the alkali metals. In the previous section, we introduced the structure and logic of the periodic table. We discussed the arrangement of elements by atomic number, the significance of periods and groups, and we began to understand trends such as atomic radius, ionization energy, and electronegativity. In this part, we will continue with a slow, detailed exploration of individual element groups. We begin with the first and lightest element, hydrogen. Hydrogen has an atomic number of 1. It is composed of 1 proton and 1 electron. In its most common form, it has no neutrons. Hydrogen is placed in group 1, above the alkali metals, but it is not considered an alkali metal itself. It is a nonmetal. Hydrogen is highly flammable and is the most abundant element in the universe, especially in stars, where it undergoes nuclear fusion to form helium. Despite its small size, hydrogen is essential for life and is found in water, organic compounds, and acids. Moving down from hydrogen, we enter the alkali metals. Group 1 elements include lithium, sodium, potassium, rubidium, cesium, and francium. All of these elements have 1 electron in their outermost shell. This single valence electron makes them highly reactive, particularly with water. The reactivity increases as we move down the group. Lithium, with atomic number 3, is the least reactive alkali metal, while francium, with atomic number 87, is the most reactive, although it is radioactive and rare. When alkali metals react with water, they form a hydroxide and hydrogen gas. For example, sodium reacts with water to form sodium hydroxide and hydrogen. This reaction is vigorous and exothermic. Alkali metals are soft and can be cut with a knife. They have low melting points compared to most other metals and are good conductors of electricity. Next to the alkali metals are the group 2 elements, known as the alkaline earth metals. This group includes beryllium, magnesium, calcium, strontium, barium, and radium. These elements have 2 electrons in their outermost shell, which makes them slightly less reactive than the alkali metals, but still quite reactive. Alkaline earth metals also react with water, though generally less violently than the alkali metals. Their reactivity increases down the group. Calcium, with atomic number 20, is an essential element for living organisms, playing a key role in bone structure and cellular processes. Magnesium is used in alloys and in biological systems. Radium, like francium, is radioactive and has few practical uses today. Group 13 begins the p-block elements. The first element in this group is boron, a metalloid. It has some properties of metals and some of nonmetals. The rest of the group includes aluminum, gallium, indium, thallium, and nihonium. Aluminum is the most abundant metal in the Earth's crust. It is lightweight, corrosion-resistant, and widely used in packaging, transportation, and construction. Gallium has an unusually low melting point and is used in semiconductors. Group 13 elements have 3 valence electrons and often form compounds with oxidation states of +3. Their reactivity varies and generally increases as we move down the group. Group 14 includes carbon, silicon, germanium, tin, lead, and flerovium. This group is notable because it includes carbon, which is the basis of all known life. Carbon atoms can form 4 covalent bonds, allowing them to create complex molecules. These include carbohydrates, proteins, nucleic acids, and countless synthetic materials. Silicon, directly below carbon, is a metalloid and is the primary component of sand, quartz, and computer chips. Germanium is also a metalloid with semiconductor properties. Tin and lead are metals with a long history of use. Tin is used in alloys, like bronze, while lead was once common in pipes and paints, but is now restricted due to its toxicity. Group 14 elements have 4 valence electrons and exhibit a variety of oxidation states. Group 15, the nitrogen group, includes nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. Nitrogen makes up about 78% of Earth's atmosphere by volume. It is relatively inert as a diatomic gas, but its compounds, such as ammonia and nitrates, are chemically important. Phosphorus is essential for life and is found in DNA, ATP, and bones. Arsenic is toxic and historically used as a poison, but also has applications in semiconductors. Antimony and bismuth are metals with low toxicity and various industrial uses. Bismuth is notable for its low toxicity compared to other heavy metals and is used in medications and cosmetics. Group 15 elements have 5 valence electrons and tend to form 3 anions, though oxidation states can vary. Group 16 is the oxygen group, also known as the chalcogens. This group includes oxygen, sulfur, selenium, tellurium, polonium, and livermorium. Oxygen is essential for respiration in most living organisms. It is the most abundant element in Earth's crust and is highly reactive, forming oxides with most other elements. Sulfur is used in fertilizers and industrial chemicals. It is known for its role in producing the distinctive smell of rotten eggs due to hydrogen sulfide gas. Selenium and tellurium are used in electronics and glass making. Polonium is radioactive and rare. Group 16 elements have 6 valence electrons and typically form 2 anions in compounds. Group 17 contains the halogens: fluorine, chlorine, bromine, iodine, astatine, and tennessine. These elements are highly reactive nonmetals, especially fluorine, which is the most reactive element known. Halogens have 7 valence electrons and are eager to gain 1 electron to achieve a stable, noble gas configuration. This makes them highly reactive, especially with alkali metals and alkaline earth metals. Fluorine is used in toothpaste and Teflon. Chlorine is used in disinfectants and the production of plastics like PVC. Bromine is a liquid at room temperature and used in flame retardants. Iodine is essential for thyroid function and is added to salt. Astatine is rare and radioactive. Halogens form salts when they react with metals, which is why their name derives from the Greek word for salt former. Group 18 elements are the noble gases. This group includes helium, neon, argon, krypton, xenon, and radon. These elements are characterized by full outer electron shells, making them extremely stable and chemically inert. Helium is used in balloons and as a cooling medium for superconducting magnets. Neon is used in lighting, argon is used in welding, and as an inert atmosphere for growing crystals. Krypton and xenon have specialized uses in lighting and anesthesia. Radon is radioactive and a health hazard if it accumulates indoors. Noble gases typically do not form compounds, although under extreme conditions, some compounds of xenon and krypton have been synthesized. Having now reviewed each major group of the periodic table, we return to the concept of periodicity. Periodicity refers to the recurring trends observed in the properties of elements. These trends include not only atomic size, ionization energy, and electronegativity, but also metallic character, reactivity, and types of bonding. Elements on the left side of the periodic table tend to be metals, which are malleable, ductile, and good conductors of heat and electricity. Elements on the right side, particularly in the upper corner, tend to be nonmetals, which are brittle when solid, poor conductors, and more likely to gain electrons in chemical reactions. Metalloids occupy the diagonal boundary between metals and nonmetals. These include boron, silicon, germanium, arsenic, antimony, and tellurium. Metalloids have properties intermediate between metals and nonmetals. They are semiconductors, which makes them useful in electronics and solar panels. Their behavior in chemical reactions can vary depending on the conditions and the elements they interact with. The periodic table is more than just a classification of elements. It is a predictive tool. By knowing the position of an element, we can infer its chemical behavior, typical oxidation states, type of bonding, and even its likely compounds. It serves as a guide for chemists, physicists, engineers, and students. It provides a framework for understanding the vast complexity of matter in a simplified, structured way. In Part 3, we will continue our slow and thorough examination by diving deeper into periodic trends, electron configurations, oxidation states, and the concepts behind reactivity and chemical bonding, all within the calming rhythm of unexciting explanation. In the previous sections, we covered the structure of the periodic table and described, in an orderly fashion, the main groups of elements, including alkali metals, alkaline earth metals, transition metals, metalloids, nonmetals, halogens, and noble gases. We also introduced the concept of periodicity, which refers to the predictable, recurring patterns found in the properties of elements as one moves across periods and down groups. In this part, we will examine those patterns, also known as periodic trends, in greater detail. These include atomic radius, ionization energy, electron affinity, electronegativity, metallic character, and general reactivity. We will also revisit electron configurations, which underpin most of these trends, and slowly review oxidation states and their significance. Atomic radius is defined as the distance from the nucleus of an atom to the outermost boundary of its electron cloud. Although the boundary of an atom is not precisely defined, atomic radius is a useful approximation that allows comparisons between elements. As one moves from left to right across a period, atomic radius tends to decrease. This occurs because additional protons are added to the nucleus, increasing the positive nuclear charge. Electrons are also added, but they enter the same principal energy level. The stronger nuclear attraction pulls the electron cloud inward, resulting in a smaller atomic radius. Conversely, as one moves down a group, atomic radius increases. This is due to the addition of more electron shells, which places the outermost electrons further from the nucleus. Even though the nuclear charge increases with the addition of protons, the increased distance and shielding by inner electrons reduce the effective attraction on the valence electrons. Ionization energy is the energy required to remove an electron from an atom in the gas phase. The first ionization energy refers to the energy needed to remove the first electron. As one moves across a period from left to right, ionization energy generally increases. This is because atoms become smaller and the electrons are held more tightly due to the higher nuclear charge. Removing an electron from a smaller atom with a stronger positive nucleus requires more energy. As one moves down a group, ionization energy decreases. The outermost electron is further from the nucleus and more shielded by inner electrons, making it easier to remove. Some exceptions to these trends occur due to electron sublevel configurations, especially in elements with full or half-full orbitals. Electron affinity is the energy change that occurs when an atom gains an electron. In most cases, this value is negative, meaning energy is released when the atom gains an electron. Elements on the right side of the periodic table, particularly the halogens, have the most negative electron affinities. These elements are close to achieving a full valence shell and readily accept electrons. Elements on the left side of the table, especially the alkali metals, have low or even slightly positive electron affinities. They prefer to lose electrons rather than gain them. As a general trend, electron affinity becomes more negative across a period and becomes less negative or more positive down a group. Electronegativity is a measure of an atom's ability to attract electrons in a chemical bond. It is a unitless value and is most commonly expressed using the Pauling scale. On this scale, fluorine is the most electronegative element with a value of 3.98, while elements like cesium and francium are among the least electronegative. Electronegativity increases across a period due to increasing nuclear charge and decreasing atomic radius. It decreases down a group because the bonding electrons are farther from the nucleus and experience greater shielding. Electronegativity helps predict bond type. When two atoms with high electronegativity differences bond, the bond tends to be ionic. When the difference is small or zero, the bond tends to be covalent or even nonpolar. Metallic character describes how readily an atom can lose electrons to form positive ions. Metals have low ionization energies and are typically good conductors of heat and electricity. As one moves from left to right across a period, metallic character decreases. This is because elements on the left side of the table more readily lose electrons. As one moves down a group, metallic character increases. This trend is especially evident in the S block and D block elements. Nonmetals, found on the right side of the table, have high electronegativities and are poor conductors. Metalloids exhibit intermediate properties. Now we revisit electron configuration. The distribution of electrons in an atom's orbitals determines its chemical properties. Electrons occupy orbitals in a specific order, starting with the lowest energy level. The Aufbau principle states that electrons fill orbitals starting from the lowest energy level and moving upward. The Pauli exclusion principle states that each orbital can hold a maximum of 2 electrons with opposite spins. Hund's rule states that electrons will occupy orbitals singly before pairing up. This arrangement minimizes repulsion between electrons. For example, the electron configuration of carbon, which has 6 electrons, is written as 1s2 2s2 2p2. The first 2 electrons occupy the 1s orbital. The next 2 go into the 2s orbital. The final 2 electrons go into separate 2p orbitals, each with parallel spins. The periodic table is organized into blocks corresponding to the type of atomic orbital being filled. The S block includes groups 1 and 2 and helium. The P block includes groups 13 to 18. The D block contains the transition metals and corresponds to the filling of d orbitals. The F block contains the Lanthanides and Actinides and corresponds to the filling of f orbitals. Each block has its own general characteristics and trends. For instance, the D block elements often form complex ions and have variable oxidation states due to their d electrons being involved in bonding. Oxidation states, also called oxidation numbers, represent the hypothetical charge an atom would have if all bonds were ionic. Oxidation states are useful for understanding redox reactions and electron transfer processes. Group 1 elements almost always exhibit a +1 oxidation state. Group 2 elements show a +2 state. Group 17 elements, the halogens, typically exhibit a +1 oxidation state. Transition metals can have multiple oxidation states, such as iron, which commonly forms +2 and +3 ions. The oxidation state of an element in a compound can often be determined using a set of rules. These rules include that the sum of oxidation states in a neutral compound is 0, that oxygen usually has an oxidation state of 2, and that hydrogen is usually +1. Understanding these patterns allows chemists to predict how elements will interact. For example, sodium, a group 1 element, will lose 1 electron to form a +1 ion. Chlorine, a group 17 element, will gain 1 electron to form a +1 ion. When these two elements react, they form sodium chloride or table salt in a 1-to-1 ratio. The predictability of this interaction is a result of their positions on the periodic table. Chemical bonding is closely related to these periodic properties. Elements on the left side of the table, with low ionization energies and low electronegativity, tend to form ionic bonds with elements on the right side, which have high electronegativity and high electron affinity. Covalent bonding occurs when atoms share electrons. This often happens between nonmetals. Metallic bonding involves a sea of delocalized electrons that are free to move throughout a lattice of metal cations. This explains many of the properties of metals, such as conductivity, malleability, and ductility. The concept of valence electrons, or electrons in the outermost shell, is central to understanding chemical reactivity. Elements in the same group have the same number of valence electrons, which explains their similar chemical behavior. For instance, all group 2 elements have 2 valence electrons and tend to form +2 ions. Group 16 elements have 6 valence electrons and tend to form 2 ions. The drive to achieve a full outer shell, often consisting of 8 electrons, is known as the octet rule. This rule guides the formation of most stable compounds, especially among main group elements. As we conclude this section, we reflect on how the periodic table encapsulates both simplicity and complexity. It is a visual summary of the underlying electronic structure of elements and their properties. Trends in atomic size, ionization energy, electron affinity, and bonding behavior all arise from the same fundamental principles: nuclear charge, electron configuration, and quantum mechanics. Despite its simplicity as a chart, the periodic table contains a vast amount of information. In Part 4, we will delve into the history of element discovery, the methods used to synthesize new elements, and the properties and challenges associated with the heavy and super-heavy elements. This will include a quiet journey through the Lanthanides and Actinides and their place in modern science. The history of the periodic table is a story of slow discovery, systematic analysis, and careful refinement. Long before the table took its modern form, humans were aware of certain elements in their natural forms. These early elements included gold, silver, copper, lead, and mercury. These elements were known in ancient times due to their occurrence in nature in relatively pure states and their usefulness in tools, ornaments, and coins. As techniques in mining and metallurgy developed, so did the list of known elements. By the end of the 18th century, scientists had identified approximately 30 elements, and the pace of discovery began to increase. In the 19th century, chemists such as Johann Wolfgang Dobereiner, Alexandre Émile Béguier, de Champ-Courtois, John Newlands, and Lothar Meyer noticed relationships between certain elements. They proposed various classifications, many of which highlighted the recurring nature of element properties. However, it was Dmitri Mendeleev in 1869 who produced the first widely accepted version of the periodic table. Mendeleev arranged the elements in order of increasing atomic mass and placed elements with similar properties in vertical columns. He left gaps in his table, correctly predicting the existence and properties of several elements that had not yet been discovered. This predictive power helped validate the periodic approach and established Mendeleev's table as a foundational scientific achievement. As new elements were discovered, refinements were made. The modern periodic table is arranged by increasing atomic number rather than atomic mass. This change was introduced after the discovery of the proton and the understanding that atomic number, not mass, determines an element's identity. Henry Moseley's work in 1913 established a more precise ordering using X-ray spectra to determine atomic numbers. This provided a more consistent and logical structure for the table and resolved discrepancies that had existed in earlier versions. As we move to the heavier elements in the periodic table, we encounter elements that are not found in nature, but are instead synthesized in laboratories. These are known as synthetic elements. They typically have atomic numbers greater than 92, which is the atomic number of uranium, the heaviest naturally occurring element in appreciable quantities. Synthetic elements are created through nuclear reactions, often by bombarding a target element with accelerated particles in a particle accelerator. This process involves overcoming strong nuclear forces, and the resulting elements are usually unstable and radioactive. They exist for fractions of a second to a few minutes or hours before decaying into other elements. Despite their instability, these elements help expand our understanding of nuclear physics, atomic structure, and the limits of the periodic table. The synthetic elements include technetium, promethium, and all elements beyond uranium, collectively called the transuranic elements. Technetium, with atomic number 43, was the first element to be artificially produced and has no stable isotopes. It is used in medical imaging. Promethium, element 61, is another synthetic element with limited applications due to its radioactivity. The transuranic elements include neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium, followed by the so-called super-heavy elements, such as rutherfordium, dubnium, seaborgium, borium, hassium, meitnerium, darmstadtium, roentgenium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, and oganesson. These elements are part of ongoing research and may one day lead to the discovery of a hypothetical island of stability, a region of the periodic table where certain super-heavy nuclei are predicted to have longer half-lives. The Lanthanides and Actinides are located in the F block of the periodic table. They are typically displayed below the main body of the table to maintain a more compact and readable layout. The Lanthanides include elements with atomic numbers from 57 to 71, starting with lanthanum and ending with lutetium. These elements are known for their similar chemical properties and are often referred to as the rare earth elements. They are used in a variety of technologies, including magnets, phosphors for lighting and displays, and catalytic converters. Despite the name rare earth, these elements are relatively abundant in the Earth's crust, although they are rarely found in concentrated forms. The Lanthanides are characterized by the filling of the 4f orbitals. Their similar electron configurations lead to very similar reactivities, making them difficult to separate from one another. They typically form SERT3 oxidation states, although some also form +2 or +4 under specific conditions. Cerium, for example, can form both +3 and +4 oxidation states. The chemistry of the Lanthanides is dominated by ionic bonding and high coordination numbers. Their compounds are often colored and can show interesting magnetic and luminescent properties. The actinides occupy the row beneath the Lanthanides and include elements with atomic numbers from 89 to 103, beginning with actinium and ending with lawrencium. The actinides are characterized by the filling of the 5f orbitals. Most actinides are radioactive and some are synthetic. Uranium and thorium are the most abundant naturally occurring actinides. Uranium is used as a fuel in nuclear reactors and as a material for nuclear weapons. Plutonium, another actinide, is also used in nuclear reactors and weapons. The actinides can exhibit a wider range of oxidation states compared to the Lanthanides, with uranium displaying +3, +4, +5, and +6 states. The chemistry of the actinides is complex and includes both ionic and covalent bonding. Some actinides form compounds with unique geometries and bonding patterns. Both the Lanthanides and actinides are essential in understanding the behavior of heavy elements and the organization of the periodic table. They present challenges in classification due to their similar properties and the need for specialized techniques to study and manipulate them. The placement of these elements in a separate section below the main table is a matter of convenience rather than strict periodic logic, but it has become a standard in chemistry education and literature. The discovery and synthesis of new elements continue to expand the periodic table. The International Union of Pure and Applied Chemistry is responsible for confirming and naming newly discovered elements. This process involves verifying the production of the element through reproducible experimental evidence and assigning a name that follows established naming conventions. The names of new elements often honor scientists, places, or properties. For example, element 114 is named flerovium after the Flerov Laboratory of Nuclear Reactions in Russia, and element 118 is named oganesson After Russian physicist Yuri Oganessian, these elements, although short-lived, help scientists explore the limits of nuclear stability and atomic theory. In addition to the physical expansion of the table with new elements, theoretical efforts have explored alternative layouts for the periodic table. Some versions arrange elements in spiral or circular forms to highlight electron configurations or recurring trends. Others attempt to group elements based on chemical behavior or quantum numbers. However, the familiar rectangular form remains the most widely used due to its clarity, simplicity, and consistency with electronic structure. It continues to serve as a foundational reference for students, researchers, and educators. As we reflect on the vast array of elements and their properties, it becomes clear that the periodic table is more than a chart. It is a conceptual framework that organizes knowledge about matter and enables predictions about chemical behavior. From the naturally occurring elements that form the world around us to the synthetic elements created in laboratories, each entry on the table represents a milestone in scientific understanding. In Part 5, we will bring this slow and deliberate lesson to its final segment, where we summarize the educational value of the periodic table, review its application in real-world contexts, and slowly conclude our extended and uninterrupted journey through the elements. As we come to the final portion of this extended and calm journey through the periodic table, we will now consider the applications of the periodic table in real-world contexts. We will revisit the structure, the usefulness of periodic trends, and the relevance of this tabular arrangement of elements to multiple scientific disciplines. The periodic table is not merely a classroom reference tool. It is a practical and predictive framework that assists chemists, physicists, engineers, and biologists in understanding matter and its behavior. The periodic table informs decisions in laboratory research, industrial production, material science, environmental monitoring, and medicine. Each position on the periodic table is not random. Each one reflects both a unique identity and a pattern of recurring properties. This structural logic allows for extrapolation, classification, and explanation of chemical phenomena in a quiet and organized manner. One of the primary ways the periodic table is used in real life is to predict how elements will behave in chemical reactions. Elements in the same group generally exhibit similar reactivity due to having the same number of valence electrons. This predictability is helpful in everything from developing pharmaceuticals to designing batteries. For example, lithium, sodium, and potassium are all alkali metals in group 1. They each have one valence electron and tend to lose that electron easily to form +1 cations. These elements are therefore highly reactive and are used in various energy storage technologies. Lithium, in particular, is essential for modern rechargeable batteries, such as those used in smartphones and electric vehicles. Transition metals, located in the D block, also have numerous applications. Their ability to exhibit multiple oxidation states and form complex ions makes them valuable as catalysts in industrial chemical reactions. Iron, copper, nickel, and platinum are used in catalytic converters, chemical manufacturing, and refining processes. Their conductive and magnetic properties make them important in electronics and electromagnetism. Copper is widely used in electrical wiring. Iron is used in steel production. Titanium is used in medical implants due to its strength and biocompatibility. Group 16 elements, particularly oxygen and sulfur, play essential roles in environmental chemistry. Oxygen is involved in combustion, respiration, and oxidation processes. Sulfur compounds are significant in fertilizers, vulcanization of rubber, and the production of sulfuric acid, one of the most commonly produced industrial chemicals. Group 17 elements, the halogens, are used in disinfectants, pharmaceuticals, and the manufacture of plastics. Chlorine is used in water purification. Fluorine is used in toothpaste and in the manufacture of fluoropolymers like Teflon. The noble gases in Group 18, although chemically inert, are not without application. Their stability and non-reactivity make them suitable for use in environments where reactivity would be undesirable. Helium is used in cryogenics and as a lifting gas. Argon is used to provide an inert atmosphere for welding. Neon is used in lighting. Xenon is used in flash lamps and in certain types of anesthesia. Lanthanides are used in electronics, magnets, and optical devices. Neodymium is used in powerful permanent magnets. Europium and terbium are used in phosphors for color displays. Cerium is used in catalytic converters and glass polishing. Actinides, while more limited in commercial use due to their radioactivity, are central to nuclear energy. Uranium and plutonium are fuels for nuclear reactors and weapons. Americium is used in smoke detectors. These applications demonstrate that even elements that are unstable and rare can serve specific and important functions. The periodic table is also an essential tool in environmental science. By examining elemental composition, scientists can identify pollutants, trace their sources, and understand their behavior in ecosystems. Heavy metals such as lead, mercury, and cadmium are monitored due to their toxicity. The chemical behavior of these metals can be predicted by their group placement and electron configuration. Environmental regulations are often based on knowledge derived from the periodic table and its associated chemical principles. In medicine, the periodic table guides the design of diagnostic tools, treatments, and pharmaceuticals. Radioactive isotopes of elements such as iodine, technetium, and cobalt are used in medical imaging and cancer therapy. Iodine-131 is used to treat thyroid conditions. Technetium-999M is widely used in imaging. The choice of these elements is based on their nuclear properties, stability, and half-life, all of which relate back to their atomic structure and periodic placement. In materials science, the periodic table is used to engineer alloys and novel materials with specific properties. Steel, for example, is an alloy of iron and carbon, often with added elements such as chromium, vanadium, or nickel. The selection of elements is based on desired traits like strength, corrosion resistance, and flexibility. Knowledge of periodic trends helps scientists select elements that will behave predictably when combined. Educationally, the periodic table serves as a foundational teaching tool. It is introduced in early science classes and used throughout advanced studies. It helps students learn about chemical bonding, atomic theory, molecular geometry, thermodynamics, and kinetics. It is printed in textbooks, displayed in classrooms, and memorized by students around the world. Its use extends beyond chemistry into biology, physics, earth science, and engineering. The periodic table also serves as a symbol of scientific progress. Its systematic layout reflects the underlying quantum mechanical structure of atoms. The arrangement of periods and groups corresponds to the filling of electron orbitals. The sequence of s, p, d, and f blocks mirrors the order in which electrons occupy shells and subshells. The presence of recurring patterns in element properties is a direct consequence of these quantum mechanical principles. The table's design is both practical and philosophical. It demonstrates that nature, at its most fundamental level, can be organized, predicted, and understood. Furthermore, the periodic table is an evolving document. As new elements are synthesized, they're added to the table. As our understanding of atomic structure improves, so does the accuracy of the data it presents. The table is dynamic, reflecting the continuous nature of scientific discovery. It is a living chart that accommodates new knowledge. This adaptability makes it not just a tool of the past, but a guide for the future. In reviewing the periodic table, we recognize that every element has a role to play. Whether common or rare, stable or radioactive, natural or synthetic, each element contributes to the structure of matter. The table provides context. It helps us understand where each element belongs and how it behaves. It gives us a way to talk about atoms, bonds, reactions, and matter itself. It is a map of the building blocks of the universe, presented not in colors and flair, but in calm, quiet rows and columns. We have now reached the end of our long, deliberate, and uneventful journey through the periodic table. We have explored its structure, its trends, its groups and families, its history, and its uses. We have done so slowly, quietly, and thoroughly. There have been no sudden jumps, no energetic excitement, and no dramatic conclusions. Only facts, structure, and a steady stream of information. And sometimes, that is enough. The periodic table is not just a chart. It is a framework, a tool, a silent, rectangular reflection of the universe's elemental order. Whether you are awake, drowsy, or somewhere in between, you now carry with you the quiet knowledge of how the elements fit together, not just in rows and columns, but in the grand design of matter itself.
If you are still awake, just immerse yourself into the background sound. Relax. Just stay here or drifting off in your own